What is the kinetic energy in electron volts of an electron with a de Broglie wavelength of 3 nanometers? We are looking for an energy. We're looking for an energy in electron volts, in eV. First thing that we're going to do is we have our de Broglie equation. Lambda equals h over mv. We're going to use this, so that's the same as h over p. We're going to use this to find the velocity. We've got lambda and we know m. We've got h, we can find the velocity. Our lambda is 3 times 10 to the minus 9 meters equals, in this case, we're actually going to be using the joule one. So 6.63 times 10 to the minus 34 joule seconds. Our mass is 9.11, 10 to the minus 31 kilograms times velocity. We get a velocity of 242,000. So a velocity of 2.4 times 10 to the 5 meters per second. That was our first part. Now, we're going to use that to find the kinetic energy. Our classic equation, K equals 1/2 mv squared equals 1/2 911 10 to the minus 31 2.4 10 to the 5. And that gets us a kinetic energy of 2.62 times 10 to the minus 20 joules. We want this in electron volts, though. So we just need to convert. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. K equals 2.62 times 10 to the minus 20 times 1 eV over 1.6, 10 to the minus 19. We get a kinetic energy of 0.17 electron volts. Up here we knew that we could use up here we knew that we didn't have to use EV, that we could use the joule one just because we didn't have electron volts anywhere else. So that is de Broglie. Electrons with a speed of 2.1 10 to the 6 are directed towards a 1 micrometer wide slit. An electron detector is placed 1 meter behind the slit. How wide is the central maximum of the electron diffraction pattern? We need to channel our inner chapter 17 for this. What we have is we have electrons traveling through a slit onto a detector. the electrons are, we have a distance, our L equals 1 meter. And we have a central maximum. Remember, when you have a single slit, you have a wider central maximum. The width of our central max is W. We had an equation back in chapter 17. The width of the central maxima is equal to 2 lambda L over A. And A is the width of the slit. We're looking for W. L equals 1 meter and A equals 1 micrometer. And we also have a velocity of 2.1 10 to the 6. We want to use this equation, but we don't have a lambda. But we can solve that. Don't let that stop you. Our de Broglie equation, H over mv equals 6.63 times 10 to the minus 34 joule seconds over 9.11, 10 to the minus 31, 2.1, 10 to the 6. We get a wavelength for the electron of 3.5 times 10 to the minus 10 meters. Now we have our wavelength. So we can now go back and use W equals 2 lambda L over A. We get a slit width of 7 times 10 to the minus 4. That's a fun one. The spacing between atomic planes in a crystal is 0.13 nanometers. 14 kiloelectron volt X-rays are diffracted by this crystal. What is the wavelength of the light? So when we have this, we're looking for, so we start with finding the wavelength. We know that energy is equal to HF, which is also equal to H times C over lambda. Since it gave us the energy in electron volts, that's what we're going to stick with. 14 times 10 to the 3 electron volts. It's going to equal 4.14 times 10 to the minus 15 electron volt seconds. 3 10 to the 8 over lambda. We get a wavelength of 8.87 times 10 to the minus 11 meters. That's how you find a wavelength from an energy. With a photon, at least. What is the first order diffraction? Our equation here is 2d cosine theta equals m lambda. 2 is going to equal 2. D is the spacing between the atom planes, which is this right there. So for D, we're going to plug in 0.13 nanometers. Cosine theta. M is the order of diffraction, so 1 times 8.87, 10 to the minus 11. We get our theta to be 70 degrees.